Hello, this is Dr. Lori. Welcome to this next main section for statistical inference and hypothesis testing. In this next group of videos, we'll be looking at some of the more focused details about statistical inference. Specifically, we'll be looking at theory, calculations, what are confidence intervals, the critical ratio, degrees of freedom, and something about the assumptions. So let's start off with a little bit of the theory. And specifically, a lot of times when we're thinking about theory, this is something that we never do. We never take 20,000 samples of a particular population and sample over and over. Sometimes I have a student ask me, now why would we do this? We would not do this. The purpose of going through this exercise is to understand how statistical inference works, the background behind it, and why we think that it's a logical way to come to a conclusion. So, we are going to play a fun game. We're going to play the mini population game. So imagine with me that we have this miniature population. It has 5 people in it. That's the entire population. That's not a sample of the population. That is the whole entire population. And they have something measured, and their values are 0, 2, 4, 6, and 8. And I've selected these just because it's going to make the math really easy and intuitive. This could represent how many cups of coffee they drink in a day, or how many books they read in a year, or how many times they take their dog for a walk each week. This is a very lucky dog. Let's go with dog walks. Okay, so this is our whole entire population. We have 5 people in our population, and we have measured how many walks they take with their dog every single week. One of the people does not take their dog for a walk. One person goes on 2 walks a week. One person goes on 4 walks a week. One person goes on 6, and one person goes on 8, so forth. Okay, so what I want you to imagine now with me is we have this mini population, and we're going to take all possible samples of size n equals 2. So anytime there's a combination that's unique, we're going to take that as a sample. So for example, I could just randomly draw the person who takes no walks and the person who takes 2 walks. So we're going to write that here. Here's R0 and here's R2. So I've drawn 2 people from my mini population, and that's the sample that I got. I got the 0 and the 2. And the sample mean for that is 1. We take the average of 0 and 2, we add 0 plus 2, divide by 2, and we get 1. Another combination, we could get 0 and 4, or we could get 0 and 6, or 0 and 8. So you can see I'm sort of systematically, I probably wouldn't draw them in this order. I could also get the sample of, I could draw the 2 and the 4, I could draw the 2 and the 6, or the 2 and the 8. I could draw the 4 and the 6, the 4 and the 8, or the 6 and the 8. And that should be 10 draws. I have now taken all, and this is going to be important later, possible samples of size n equals 2. And if we calculated the average for each one of those samples, we have 10 samples, the averages would be, the average of 0 and 4 is 2, average of 0 and 6 is 3, average of 0 and 8 is 4, average of 2 and 4 is 3, average of 2 and 6 is 4. See how I made this easy so that we could get the averages pretty quickly. Average of 2 and 8 is 5, average of 4 and 6 is also 5, average of 4 and 8 is 6, average of 6 and 8 is 7. So we started off with a population, and we took all the possible samples of a specific sample size, n equals 2. Now, statisticians have special names for some of these, and so you'll see this sometimes in the literature. If we drew, say, this particular sample right here, we could call that the sample mean is x bar, x with a bar over the top. And so we could call that x bar 1. This next one, we could call that x bar 2. And we would name these 3, 4, 5, 6, 7, and so forth, all the way down to x bar n. And because my n, or sorry, not n as in this n, but sample size, or the number of times that I've drawn samples, I have 10 of these samples that I drew, so this would be all the way down to x sub 10, if that makes sense. So x bar sub 10. Now, if I take the average of this mini population, I would take 0 plus 2 plus 4 plus 6 plus 8, add those all up together, which is 20, and I would divide that by 5, and so my mean is equal to 20 divided by 5 is 4. If I were to take the average of all of these sample means, I would add these all up, 1, 2, 3, 4, 3, 4, 5, 5, 6, 7, and I would actually get 40. You can check my math if you'd like. And since I have 10 sample means, I would divide that by 10. And again, my mean of the sample means is also equal to 4. And so this is an important feature of this collection of sample means that I've done, is that the mean ends up being the same. So my mean is 4 dog walks per week, and my sample means end up having an average of also of 4. And you'll notice one of the interesting things is you'll notice that this is a pretty flat. You know, if you had some kind of distribution, it would just be like flat. It doesn't go, it's not like curved. It's definitely not that. So we have now demonstrated that this middle point is the same for both the population and for this collection of all these possible samples. Now that collection has a special name, and it's actually called the sampling distribution of the mean. So in other words, I have taken a hypothetical. Remember how I said we never do this? This is not an actual activity that biostatisticians partake in. So it's hypothetical. We never do this. Distribution of all, remember how I said this is important, all possible, and they're all the same size, sample means taken from a population. So usually we think of this more in terms of what if I had a population, say, of 100,000, and I take a bunch of samples of 100 people. I draw 100, put them back. I draw another 100, put them back. I draw another 100. I do that over and over and over and over. Of course, hypothetically, we never do this. I repeatedly take samples of size 100. What happens when I do that? Well, let's take a look at what happens to our little mini population first. For this, now that we have a word for a sampling distribution of the mean. So if we look at the actual sample means that we got, and that's right here, I got a 1, so I'm going to draw a little 1 here. I got a 2, so I'm drawing these on basically like a histogram. I got a sample mean of 3. I got a 4. I got another 3. You can see I'm kind of starting to build this. I got another 4. I got a 5. I got another 5. And I got a 6 and a 7. So here's my 6 and here's my 7. And so the thing that I want you to notice, this original population here, it was actually what we would call a uniform population. It was flat. It did not have a higher middle or a higher anything else. But the sampling distribution of the mean has a different shape. It tends to start to group a little bit near the middle. if we were to smooth that out. Now you can imagine then, if we go to our other scenario, what if we had a population of 100,000 and we take these repeated samples of size 100? What we actually end up with is exactly the same kind of thing that we saw in the normal curve. So our new sampling distribution of the mean starts to look like a normal curve. And the more the sample you have, the more it looks that way. In fact, as soon as you get to about 30, you have a pretty normal curve distribution. So when we're talking about doing all this hypothesis testing, we're talking about this whole concept, this notion of having a sampling distribution of the means. And so we're going to be going into that further. If the population mean is here in the middle, what we find then also by doing this repeat sample is the mean, and I'm gonna draw a new thing, the mean of these x bars. Remember how I said we call this x bar? The mean, I guess I have to come back here. We'll get rid of that. The m sub x bar, the mean of the sample means, is also located in that same exact spot. And there's a reason that that happens, and I want to point it out to you with our tiny population. Once you see this, then you'll see why this makes sense. In our mini population, we had a 0, a 2, a 4, a 6, and an 8. And when we did our random samples, we have 4 zeros, we have 4 2s, we have 4 4s, we have 4 6s, and we have 4 8s. So it makes sense if we draw all of them an equal number of times, then we will end up with the same number here as we have here. So that concludes this introduction regarding the theory. Remember that concept, that name, sampling distribution of the mean, because that's going to come up over and over and over. That's what we've done. A hypothetical distribution of all possible n-size sample means taken from the population. So thank you for joining me, and I'll see you on the next video.